Ladies and gentlemen, welcome. On behalf of the UCSC Emeriti Association, I'm pleased to see you come out and enjoy this lovely evening, for one thing. And we have to present to you tonight one of our Emeriti lectures. This lecture series was organized in order to let us share with you and the community some of the insights and wisdom generated by the senior faculty at UCSC. The series is supported by Chancellor Denise Denton, for which we are grateful for her support. And also, it wouldn't be possible without the dedicated work of the special events coordinator, Kristen Palma, and her associates. So we thank Kristen very much for her work bringing this series together. Tonight's lecture is being given by Professor Emeritus Michael Nauenberg. The title of his talk is The Nature of Science and the Science of Nature, an Historical Perspective. We'd like to remind you that after the lecture, there will be light refreshments served right here toward the back of the room, so we invite you to stay and chat and talk with the lecturer if you like. Also, there will be an opportunity for you to ask questions at the end of the lecture, and we would like for you to use the microphone that's over here on this side of the hall. When you do ask a question, the lecture is being taped tonight, and we'd like to include the question and answer part of it as well on the tape. Professor Nauenberg will be introduced by Professor of Mathematics Anthony Tromba. And so, Tony?
Thank you. Can you start there? Great. Well, good evening, everyone, colleagues, ladies and gentlemen. It's a great pleasure to see the faces of many of my colleagues, some of whose friendships were made during those challenging and stimulating early years of our college system. I am truly honored to be able to introduce a colleague and a friend whom I've come to regard with ever-increasing admiration since our first meeting on the Cowell Knoll 36 years ago. Michael Nauenberg studied physics at Cornell under Hans Bethe, one of the great icons of 20th century physics. He came to UCSC in 1966 as a founding member of our physics department. So he has had a very distinguished research career specializing in particle physics, condensed matter physics, nonlinear dynamics, and the history of science. The current high stature of our physics department is in no small part due to his efforts. I should also say that Michael has a theorem in quantum field theory, very esoteric subject, named after him, Lee Nauenberg theorem, and very few, I'm a mathematician, that's a very, very big thing. Very few people get the chance to have theorems named after them. His extremely high intellectual standards and his unyielding sense of integrity have served our campus well during its first, sometimes tumultuous 40 years. As a young professor, as I witnessed Michael in action, I became keenly aware of how important faculty with his intellect, integrity, and courage are to the success of academic institutions. His advice and insights were usually invaluable. An example: it was March 1989, the first days of the national uproar over the discovery of cold fusion at the University of Utah by Fleischmann and Pons. Billions of dollars in revenues were said to be at stake. Over lunch at Crown, I told Michael that the Dean of Science at the University of Utah, with whom I served on the board of one of our national institutes of mathematics, was deeply involved as an administrator in this startling new development. Michael didn't hesitate. If he's a friend, get on the phone immediately and tell him it's all a scam. I took his advice, but unfortunately for Utah, their dean did not. We are here to learn something about the history of science. How am I doing? Oh, that's the wrong picture. Oh my God. That's my punchline. Oh God. Okay. Okay, so we're all here to learn something about the history of science. One of our disappointments, that's why I like real slide projectors, you know, you're pushing the button. We are all here to learn something about the history of science. One of our disappointments in the early years at UCSC was that we, during the most active period in history, neighboring the epicenter of modern technology, failed to develop either a history of science program or a science-based college core course. Michael, even before his research in the history of science began, vigorously supported having this field develop on our campus, and has continued to support bringing people actively interested in the history of scientific thought together. The truth is that many of us take a short-sighted and somewhat prejudiced view towards the history of science and mathematics. And therefore, simply put, it is neither research in physics nor mathematics, and therefore ranks as a low, very low priority. Thus, historical work has been left mostly to historians, some of whom may not have the scientific training to deeply grasp the work of our predecessors. As a result, errors and misunderstandings have crept into the historical record. And this record is not as complete as it could be. This particularly pertains to the beginning of it all, the time of the culmination of the scientific revolution, during the period of the Baroque and the Rococo, from the end of the 17th through the 18th century, a time when science and modern mathematics were born. It was the time of Newton, Hooke, and Leibniz, three of the greatest geniuses to grace the face of the earth. It was the time of Newton's Principia, the Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The Principia, written in Latin, was often celebrated as the foundation of modern science, but rarely read, and when read, not truly understood. Consequently, the profundity and magnitude of Newton's genius was often never fully grasped. During the last decade, I have watched in awe as Michael set about the task of applying his scientific expertise to the understanding of the contributions of giants like Newton and Hooke. The importance of his work has been internationally acknowledged. His success has been astounding. In just a few short years, he has been recognized as an eminent Newtonian scholar, being invited by the Royal Society to co-organize a meeting on the foundations of Newtonian scholarship, and that's the book that's a result of that wonderful meeting. Both of us share this fascination with Newton, and I have learned much from Mike. Ever so often, after a conversation, I have to run off and rewrite sections of my vector calculus book. There you go. And you could see a similarity, maybe plagiarism, maybe this will be handled in the British courts, or let's go back, just a joke. We both love Newton. Michael has demolished the commonly cited cliche that Newton, who along with Leibniz invented the calculus, never actually used calculus in the Principia. You can read this in every book you open, it says that. In fact, I paraphrased that in my own works. I was thrilled as Michael led me step by step through Newton's own words, illustrating that Newton's reasoning, disguised for most observers, was really calculus after all. In looking at the past, Michael has also contributed to current scientific research. Using new insights into Newtonian mechanics, he, along with my colleague Richard Montgomery and co-authors, have discovered stunning new potential configurations for planetary systems, some of which you can see on his website, michael@mike.ucsc.edu. So it is with great pride for our campus that I welcome Professor of Physics and eminent historian of science, Michael Nauenberg.
How do I switch you off? All right. Let me go one step back here. Right. Well, thank you very much for that nice introduction. I don't know whether there's any need for me to give any lecture anymore. I'm very pleased to be here tonight, and I thank you all for coming. Tonight I would like to talk about the nature of science as seen through the work of Robert Hooke, the most prolific scientist of the 17th century. And I mean prolific. I can almost think of no one else in the history of science that did as much work on so many different fields as Robert Hooke. At the start of modern science, Hooke made very important contributions to virtually all scientific fields, while also being a great architect and the surveyor who directed the rebuilding of London after it was destroyed during the fire in 1666. Only very recently have the documentation been discovered, and a whole book on the subject has been written. Yet Hooke is virtually unknown today, except by a few connoisseurs like Tony. During the course of this talk, we will see how and why this forgetfulness happened. But certainly one of the major reasons is that he gained the long life enmity of Isaac Newton because he dared to criticize the great man's work. In the course of this presentation, I also will discuss some of the arguments against science, which we hear today, but have a long historical background. And these very arguments against science were made at the beginning of the scientific revolution. I was planning not to mention any of the well-known contentious disputes that I mentioned here, but I can't help it that this morning headlines, which you probably you have all seen, illustrates very clearly the nature of science by providing new evidence for Darwin's theory of evolution. Can I have a show of hands? Everybody has seen this, I presume, and read it. We have just another one of the predictions of a theory. And science is not just about explanations, but about predictions. I just thought, I came across the statement of the philosopher John Dewey, which I thought was very interesting because the controversies that we hear about today have a historical background. Dewey says the Darwinian principle of natural selection cuts straight under this philosophy, that of design. There is no call for a prior intelligent causal force to plan and preordain organic adaptation. Hostile critics charged at Darwin with materialism and with making chance the cause of the universe. Well, last night I had dinner with our speaker from Holland, and the Dutch are in the middle of a controversy, just like we are too, on this subject. And this is about 100 years ago. Now, I said Robert Hooke is virtually unknown, but I think soon this will no longer be the case. There are now no less than 6 new books that have been written within the last 3 years, recounting his achievements. And if you go back 10 years, there are almost a dozen. I myself wrote very early on an article about it when I, like the rest of us, knew nothing about him and began to discover what an absolutely fabulous man he was. I know I drove my family crazy because of my passion for Robert Hooke, and I apologize for that, but I hope by the end of the night to convince you that there is indeed a great deal to be said. Now, one of the books by Lisa Jardine, who is a superb historian of science, has a portrait alleged to be a portrait of Robert Hooke. In fact, it's now been well established that this is not Robert Hooke. I called Lisa and I said, how did you find out? I thought that there were no portraits, and I didn't call her. I sent her an email, and she didn't respond. Maybe the publisher wants to have pictures. We need pictures to recognize our great men. In fact, all our great men have pictures. Robert Hooke doesn't have a picture because it's rumored that Isaac Newton, when he became president of the Royal Society, destroyed the known portrait. But it's a rumor. I don't think there's clear evidence about this. Now, it's interesting that now Hooke is referred to as the Leonardo of England, the Leonardo of London. And I think that it's a well-made comparison. But I'm truly convinced that when it comes to the scientific aspects, the Leonardo of England had it over the Leonardo of Italy. I particularly wanted to show you this, the frontispiece of this book, because you see here the famous experiment from which Hooke came to the law of elasticity. You see a spring, and you put some weights, and you measure the extension of the string as you increase the weight, and you find a linear relation, which is called Hooke's law. And in the textbooks, in physics at least, that's the only thing you ever hear about Hooke, that he contributed Hooke's law. Over here you see another spring, but this time it's a circular spring. And again, it obeys Hooke's law. And I'll come back in a minute to that. Excuse me, I have to move forward. Here is another recent book. In fact, this is the latest book, which is based on lectures given at the Royal Society at the 300-year anniversary of the death of Robert Hooke, in which I participated, and this is a compendium of our contributions. I wanted to just show you yet another one of numerous apparatuses and experiments. Here is an experiment, the apparatus, where Hooke basically wants to measure the force of impact, dropping a ball and watching the consequence of this. Many of you probably have heard the news a month or two ago that some papers, original papers of Robert Hooke, had been discovered in a cupboard of an old house in England. I rushed over to London to see these papers because they were going to be put on auction, and I was afraid that Bill Gates will buy them and we'll never again have a chance to look at them. Turns out these are minutes of the Royal Society. Hooke was the curator of the Royal Society in its beginning, and in fact he was practically the soul of the place, kept it together. The people in attendance were mostly, wealthy people who wanted to be entertained as well as learning the new philosophy of science. And so here you see, I particularly show you the opening page here because of this spring. What you see on the left, on the right-hand side, I will show you a expansion, is the fact that Hooke had invented a spring watch. I don't know if you can read this in the back, but let me read it for you. It says the curator, this is the minutes, in 1670, the curator produced a pocket watch of a new contrivance probably it's easier for me to read it here, of a new contrivance devised by himself, which he affirmed should go equally as a pendulum, in other words, as a pendulum clock, and without stopping for at least 8 days. The reason why it's interesting is because in Holland, everybody says that their great scientist, Christian Huygens, invented the spring watch, and there's been a controversy in the history of science literature for decades of who was first. Well, I think we now have some strong evidence that it was Hooke, and it was the Secretary of the Royal Society, Oldenburg, who communicated his idea to Huygens. And if you read some of the correspondence of Hooke, he always referred to Oldenburg as the dog. He was well aware that these minutes were not transcribed by Oldenburg, who was the secretary, so we didn't know about it until it appeared in these manuscripts. While I was in London, they invited me, and I was very honored, to give a physics talk at Westminster School, which is one of the oldest schools in London. And it was a school where, as a young boy, Hooke learned, his stuff. So I was extremely pleased, and it was very nice. And at the end of my lecture, they gave me an honorarium, which you see on the. Now, this is a very interesting honorarium, a very interesting, because it shows, I'm not used to this yet. I'll learn fast. You see Isaac Newton with his famous prism where he broke colors. You see the telescope, which first made him famous, the Principia. And over here you see his most famous result, namely that the planets move around the sun in an ellipse. Does anyone see anything peculiar? Any physicists in the audience, astronomers? Excuse me? It doesn't have the sun in the center. The ellipse doesn't have the sun in the center. And the embarrassment of the Bank of England. The sun is, of course, at the focus of the ellipse. And the Bank of England had mud in its face, had promptly had to withdraw this. And so I think this is worth a bit more than £1 now because it's hard to get. Now, when I came here shortly before Tony, I was a member of Crown College, and we used to have core courses. And Kenneth said, look, we need some books for the core course, and we will start our core course in the sciences with the famous book of Thomas Kuhn, who is considered one of the great philosophers of science of the past century. I put down a quotation from his book, which is very interesting. He says, scientific knowledge, like language, is intrinsically the common property of a group, or else, and this is my emphasis, nothing at all. To understand it, we shall need to know the special characteristic of the groups that create and use it. Well, to scientists, this sounds totally weird because we think of scientific knowledge as universal, and it matters very little who, or other than for personal reasons, which groups create the knowledge. But Kuhn is, the modern guru of people outside of the science. Science is about science, and I'll have more to say about later. In particular, I will mention more about this book. There was a scientific revolution, and Steve Chapin, who is now a professor of history of science at Harvard University, starts his book by saying, there was no such thing as a scientific revolution, and this is a book about it. In other words, it is a book about nothing. Of course, the rest of the book is pretty standard stuff, except when I looked, and Tony, you will like this, when I looked at the appendix, of the index of the book, for the word calculus, I didn't find it. There's not a word about calculus in the entire book. And I was very surprised. And he says in the book, I can't find the essence of the scientific revolution. So I saw him at a conference in San Diego, and I said, Professor Chapin, why did you leave out the calculus? And he stared at me, just no response. Of course, the calculus is one of the two of the essence of the scientific revolution. Without the calculus, modern science is not possible. Those of us who grew up as scientists in the scientific, I think would all share with another historian, an earlier historian of the origins of modern science, Herbert Butterfield, who said that the scientific revolution, which is nothing at all to Chapin, outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, mere internal displacements within the system of medieval Christendom. Well, perhaps that's a bit exaggerated, but in 1,000 years, I think we will probably still remember. Now, I want to put on two quotations here because they give a kind of a different impression of some of the old-timers. Aristotle, because we physicists often make fun of Aristotle because all his physics was wrong, but he did appreciate the importance of observations. On the other hand, to punish you for the loss of a sense if you don't use it, I think it would be, I thought about it and said, look, we see the sun rise, it goes around, goes down. So therefore, for thousands of years, people thought this sound, that's what their sense told them. So Copernicus should lose his sight because he said it's not the sun rising, it's us turning around. The sun is, we're moving, and the sun is standing still. So one has to be careful. Gottfried Leibniz, who is one of the greatest mathematicians of all times, said, I prefer a van Leeuwenhoek who tells me what he sees to a Cartesian who tells me what he thinks. Van Leeuwenhoek, of course, was a very famous Dutch microscopist, one of the pioneers in microscopy, and I will say more about him later. But even Leibniz, who was supposed to be 100% Cartesian in his philosophy, realized that observations are important. And of course, science is important. Observations is what is most important about science. Now, what are the major factors in the rise of modern science? I mean, why the 17th century? Why a bunch of, countries out there in Northern Europe, and in particular, short span in the history of mankind, there is this enormous explosion of ideas which form the basis of modern science. And I like to suggest two important developments. One of them was the development of new instruments, which extend the senses that Aristotle was telling about. See, until then, our senses were our eyes, our ears, we touch things, but that gives us a very limited view of the universe in which we live. And now there was the telescope, which opened up the heavens. There was the microscope, which allowed us to see at the smaller scales. And accurate clocks were extremely important. The fourth one, you may be surprised, the air pump. Why was the air pump important? And in fact, I'm going to talk at the end primarily about the air pump. And the reason it was important is because there was enormous dispute over centuries about the nature of the vacuum. I mean, is there such a thing as empty space? What's there between the Earth and the rest of the universe? Is it empty, and can emptiness? Aristotle said there can't be a vacuum. What's the word? I abhor vacuum. And scientists continuously came up with ideas about the vacuum, and we will talk about that. It's interesting because even today, well, first of all, I should remind you that the vacuum was filled with ether for a long time because it needed to propagate light. Aristotle understood there can't be a vacuum because light propagated through space. So how can light propagate if there is a vacuum? And we had an ether until the turn of the last century, when finally Einstein told us that it wasn't necessary, and everything could be explained very nicely with the special theory. But then our modern cosmologists have rediscovered that the vacuum is full of energy, dark energy. Can't see it. It's there, dark energy. Not only that, it's most of the universe consists of energy in the vacuum. So we're back, and that's why the historical perspective, I think, is somewhat helpful. We're back to having the vacuum filled with something, although we never know what that is. So nobody knows what dark energy is, but we can talk about it. By the way, if we can talk about something that is very important, give it a name, and there it is. The second, of course, important development that Chapman doesn't seem to realize is that there was an explosive burst in the understanding of mathematics. And Galileo himself said that nature's great book is written in the language of mathematics. I put it in his home language, Italian. He says, and the characters are triangles, squares, and geometrical figures. You see, it's easy to translate language, whether Greek or Latin or French or Dutch, but we can't translate mathematics. Mathematics is a universal language, and you have to learn that language if you want to understand science at a deeper level, and unfortunately, that is not a common language. And so a lot of the problems of understanding science is our limitations in not being well aware of the language. I think, Tony, you like this one about James Jean, that God is a mathematician and a physicist.
That was repeated by Paul Dirac.
And it was repeated by Dirac.
And I repeated it to many deans who looked at me with horror.
Horror or heretic to say that. But it is the universal language of nature. And Wigner, who was one of the great pioneers, puzzled correctly about why is mathematics so effective? Why is it the language? I just noticed on my email the conference that I often attend in the East Coast that Joe Lebowitz has every year on statistical mechanics, and they're going to have a round table, and guess what they're going to be discussing? The unreasonable effectiveness of mathematics in science. I mean, we don't understand why mathematics is so effective, but that is what we have learned. Here is one of the earliest printed versions of Euclid, and you can see the figures that Galileo was talking about on the right-hand side, circles, triangles, squares. Here is a page of the great mathematician Archimedes, and also a polymath. And I think that is this method of exhaustion, right, Tony? Presented on the left, where he approaches a circle by a sequence of interior, and it's in Greek, but the language is universal. And don't forget that the greatest book on an invention of algebra was an Islamic invention. And I dare not pronounce the name of the author, but this was, the entire book, by the way, is written in words. I understand it's very hard to read. Now, let's go back now to the instruments. I mentioned the telescope, the microscope, the clock, and the air pump. And you notice from my picture that of those 4 important instruments, 3 were developed by Robert Hooke. I mean, he was the first one to use a microscope, and he certainly built the air pump, which we will say a lot more about later, and the spring watch. Huygens, of course, anticipated with the pendulum clock. So there was a fight about who can build the best clock. And Christian Huygens, who is the greatest scientist of that period in Holland. And then, of course, we have, we have Galileo's telescope. By the way, the telescope was actually developed, was invented by people in Holland. The exact nature of who the inventors are is not that well known. But what Galileo did, and so the telescope was something you could practically shop for in the streets. But what Galileo did was very important. He played with the lenses and made the magnification sufficiently great that he could make important discoveries. And that was, of course, the important thing, is to make it into a scientifically useful instrument. I just put down for future references that Hooke was, above all, a philosopher of nature and expressed the importance of doing experimentation. Now, let me contrast, because this is very important, let me contrast at that time the attitude of Robert Hooke and others with the attitude of an important philosopher, but he was a philosopher of government and politics, Thomas Hobbes. And here is what he says, and I quote from his book, Dialogos Physicos. He says, "Why all this apparatus, all these instruments, and the expense of machines of difficult manufacture, just so you could get as far as Hobbes had already progressed? Why did you not rather begin from where Hobbes, left off? Why did you not use the principles that I established? Whoever sucks water into his mouth through a tube first sucks the air in between, which being removed cannot have a place. So it has to be filled in with something. Can't be a vacuum, it has to be something. They used to call it a plenum, except by moving, etc." In other words, he was talking about the familiar effect. I don't know, maybe you all know this, right? But I'm going to talk more about it. I mean, this looks all extremely trivial to you and everybody. I suck my juice with a straw, but if I close it up at the top, not only does the water come up, it gets sucked by Hobbes' plenum, but it gets even stuck. And of course, if I open and let air back in, the plenum goes out. Well, this triviality puzzled and was not understood by people for centuries. In fact, I will show you that even some great scientists, like Galileo himself, believed that you were sucking, when you sucked the air out, the vacuum was full of force, energy, as we would say today, which attracted the water like the water would stick to the vacuum, and you could pull it up. Before I show you Galileo's on that, I found it very amusing that Hooke actually met Hobbes. Hooke was very, very social. He would finish his work and he'd be at the cafes and he met everybody. there was anybody in London at the time. And like Pepys, the diarist, you know, he kept a diary, so we know a lot about it. This was actually in a letter, and gives a nice, interesting portrait of Hobbes. He says, I was a little surprised at first to see an old man to view me and serve with me in every way without saying a thing to me. But I quickly shaked off that surprisal when I heard my Lord call him Mr. Hobbes. Suppose that he had been informed who I am, or as he say, who I belong to. Well, the English of the time. I soon found by staying the little while he was there that the character I had formerly received of him was very significant. I found him, you know, making these assertions. Every assertion he made, there was a round oath. He undervalued all other men's opinions and judgments to defend to the utmost what he asserted though never so absurd, to have a high conceit of his own abilities and performance, though never so absurd and pitiful, etc. For example, Hobbes asserted that the common glass was as good as a 36-foot telescope. You could see the same with both. And he did all this, shaking and so forth. Hobbes was refused admission to the Royal Society at the time, I presume because Hooke's opinion was shared by others. However, let's hear what contemporary people have to say about him. And I bring again Mr. Chapin and his collaborator Schaffer, who wrote a book called Leviathan and the Airport. Leviathan, remember, is the book by Hobbes. And the conclusion of the book is surprising. Hobbes was right. Hobbes was right in an interaction with Robert Hooke, Boyle, and others. And what do they say? They say Hobbes' criticism is that no matter of fact made by experiment was indefensible, since it was always possible to give a rival account. Experiments don't prove anything. You can always figure some other explanation. So what's the point of it? Or else, and now is the voice of Chapin and Schaffer. As we come to recognize the conventional and artifactual status of any of our forms of knowledge, we put ourselves in a position to realize that it is us, ourselves, and not reality out there, that is responsible for what we know. That's the prevalent view in many communities, including in some corners in our own community at UCSC. And sometimes it goes under postmodernism, post-structuralism, and what have you. And we teach students things like this as an expression of science. This book has just won a prize. Last year it was regarded, it's a very famous book. It's a must-reading in science studies courses, but it reaches absolutely, I think, erroneous conclusions about the nature of science. And we have a problem here because when we don't understand the nature of science and we teach it improperly, we're raising some problems. Here, by the way, is the cover page of the paperback, which shows Hobbes. On the right-hand side, he has a sword, and on the left-hand side, this isn't the actual original, but on the left-hand side, he has the pump that we have seen, and obviously, Hobbes, the dragon's slayer, right, is cutting off the pump of Robert Hooke's. So the message is unmistakable that Hobbes is right, and we don't need those pumps and all that. Now, I said at the outset that we want to understand why is Robert Hooke so little known. This is a portrait of Mr. Boyle And Boyle is famous in chemistry and physics for his so-called, for the Boyle law, right? That pressure times volume when you compress air is nearly a constant. Boyle wrote up his experiments, 40 experiments he did in a famous book on the compression, on the properties of air. And you see in the background a pump, but it's Robert Hooke's pump, not Boyle's pump. Hooke built the pump, and Hooke was the collaborator of Boyle, but he's not mentioned. Well, I would say he's almost entirely not mentioned through the entire write-up. Well, Boyle had been paying Hooke's salary, and in those days, and we know many stories of that kind, right, Tony? Bernoulli was paid by L'Hôpital, who wrote a whole entire book on calculus based on the Bernoulli's lectures. And so we call it Hospital rules and the Hôpital here and there, and it's all someone. And those in the older days, you know, if you could pay someone to do things. But certainly Boyle's PV law is certainly due to the work of Hooke. In fact, as I understand it, Boyle, first of all, didn't know very much of mathematics. He couldn't even have the idea of expressing a mathematical relation was probably over his head. Anyway, I don't want to go too far in it, but you know, if you write a book and you don't credit. Hooke, by the way, did get back, and he inserted his results. He repeated the experiments and published them in a famous book called the Micrographia, where he, in fact, mentions that here are the tables of numbers in which experiments, I think, may safely conclude that this is a word for pressure of the air is reciprocal to its extension. But he's not credited at all. One of the things I often do when I'm visiting, while I was visiting in London, I go to bookstores, and I asked the man, I said, they have a lot of old books. I said, you have any books about Newton? He said, oh, he handed me this book. And I opened it. First thing I see, lo and behold, when I open the book, I see a pump. This is just a modernized version of Hooke's pump. You know, you have a bell jar, and you have a pump here. Here things are disconnected, but this is Hooke's pump. But what's the title of the book? A Course of Experimental Philosophy, an Introduction to Philosophy of Newton. Newton never did any air experiments. There's nothing, and when I read the book, there's no mention of Hooke whatsoever in it. So how did Hooke get forgotten? I promptly bought a copy of the book, and when I came back to the hotel, I got a frantic call from my wife. Our visa is being blocked. Did you lose your visa? I said, no, probably I spent a little too much money. At which point she says, I'm going to faint. And she hung up. Am I forgiven now? Anyway, you can again see an example of why Hooke disappears from sight, and Mr. Newton starts getting credit for things that he even had nothing to do. I don't know the author of the book, but he's a teacher of mathematics in Dublin, and he wrote this book shortly after Newton died. Let me show you some pages of the book that Hooke wrote, the Micrographia, because it is an absolutely marvelous book. You know, the famous diarist, 17th century diarist Pepys, who, by the way, often came to the Royal Society, got a copy of it and reported in his diary that when he got it, he couldn't go back to sleep. I mean, he spent the whole night till 2 in the morning reading it. And you'll see in a moment why, because the book not only has, here again is the microscope. Incidentally, Hooke grinded his own lenses, which is very important because lens grinding is essential, and in those days there were no lens grinders. And here, by the way, is another picture of an instrument that he developed called a barometer, which I haven't bothered to mention. Now look at these beautiful pictures that he saw on the microscope. With magnification of this fly, he could see things that were invisible to the naked eye for the first time. I mean, and look how beautiful his drawings are. He had learned how to paint very well. And of course, it's very important when you look through a microscope and you don't have modern photography to be able to reproduce what you see. And Hooke had the ability to reproduce what he saw. This is probably his most famous picture. Many of you, no doubt, have seen it, of a flea. But what you may not have seen is the writing. I mean, it's poetic how he describes what he sees. I mean, the strength and beauty of this small creature, had it no other relation at all to man, would deserve a description. And he describes it, for example, he describes the curiously polished suit of sable armor and so forth. And he describes how the legs work. And it's all magnificent. And the book was a tremendous success. And of course, it was read widely. And one person who read it was none other than the man who is regarded as the most important man with microscopy, Van Leeuwenhoek. And he was inspired to build his own telescope, his own microscope. You see, his microscope was curiously much simpler. I won't describe it now, but it had quite a magnification. And I'll just mention one important discovery that Van Leeuwenhoek made was discovered the currents of sperm. And he drew it, he made the drawings. And when they came to the attention of our physicist friend Christian Huygens, he rapidly reproduced them because Van Leeuwenhoek was really just, he worked on textiles, he had no scientific training or anything, so Christian Huygens wanted to make sure that the Dutch were the first to discover it. Another thing that Hooke, who was enormously curious about everything, he was very curious about ammonites and their origin. Let me just, and again, he drew beautiful pictures of what he saw, and let me tell you what he said. We will, for the present, take this supposition to be real and true, that there have been in former times of the world diverse species of creatures that are now quite lost and no more surviving upon any part of the earth. And yet, I do not see how this doth in the least derogate from the power, wisdom, and providence of God, as is alleged. See, already the conflict between the biblical version and the evidence of these fossils was in conflict, and there was a conflict. The effect of petrification is a symptom of old age. Now we all know that. Emeriti know that. No less capable of proof and confirmation than histories of records are by coins, inscriptions, and monuments. He knew that you could learn about the history of the world by studying these things. And does he get great credit for it in geology? If you look at geology books, they talk about Nicolas Steno, who was a Danish. And as far as we can see, that Nicolas Steno, again, knew about Hooke's work, may have been stimulated by Hooke, but he gets, I think, the lion's share of the credit. Now, before embarking on, let's see how we're doing on time. Of course, you took a long time, so that doesn't. Let me just go very quickly over everyone knows that Ptolemy made a marvelous model of how planets move in space and wrote a book about it. It's probably the greatest book on applied mathematics. I spent the summer reading it, and I was just absolutely astounded at the amount of mathematics, including, having to deal with small quantities. I mean, he didn't have limits, but he certainly understood, because you had to have the concept of velocity and so on. So he understood that you had to take he took Euclidean geometry to a very high level. And he produced a model, which I will discuss briefly with you, where the Earth was standing still and the planets were moving around. And of course, every schoolboy learns that Copernicus came along and showed that, in fact, the Earth is not standing still. The sun is standing still, right? The sun is standing still, and the planets, including the sun, the planets, including the Earth, are moving around the sun. And so Ptolemy was wrong, and clear evidence of now, it's curious that some 27 years after Copernicus' book, the two theories, Copernican and Ptolemaic, were taught side by side at the University of Oxford. There was astronomers did not make immediately the notion that one of them was preferred over the other. And let us see why. I think this is generally not well understood. Let's look at Ptolemy. Ptolemy says the Earth is standing still. We draw it in green. And the sun is rotating around the Earth. Here's the sun. The sun is rotating around the Earth. And Venus is rotating around a point such that the sun and the Earth are always lined up. Here is a time motion of that picture. Okay? So we see the orbit of Venus and the sun around the Earth. Here is the picture according to Copernicus. The sun is standing still, the yellow sun, and Venus is rotating around the sun, and the Earth is rotating around the sun. Now let's put them together side by side, and what happens? What do you notice? Is it clear that the relative motion of the two is identically the same? There's no way to distinguish by observation which is the right model, at least not from the point of view of motion and observation that's just based on motion. So the astronomers had no reason to prefer one over the other. If you read Copernicus' book, it is, from a mathematical point of view, I found it totally amazing. By the way, people generally don't read those books, so they talk about these things and never look at the book. You look at the book, you find that what on earth did it take 40 years to Copernicus to write a book like that, when all he did was changing the frame of reference? I mean, it's a piece of cake mathematically, the mathematics. Okay? The idea, by the way, was also not original, but the mathematics was a piece of cake, and yet 40 years of work. And so the great Copernicus, worked for 40 years. It was Ptolemy who did it. In fact, there are places in which Copernicus' book where he works things out according to the Earth standing fixed, because he also borrowed things from the Arabs, but I won't go into any details. If it is mathematically, the two models are the same, and there is nothing from that point of view to prefer one over the other. Of course, physically, when we start to talk about dynamics, things are somewhat different. Not in general relativity, because there again we go back to the equivalence of the two. But at least in Newtonian physics, there's a great deal of difference between the Earth moving or the sun moving. Now, everyone says Galileo cleared things up because he pointed the telescope and guess what he saw? He saw the phases of Venus. So the phases of Venus imply the sun is not outside, but it means that Venus is clearly circling the sun, and that proves the Copernican theory. Not at all. All that proves is another old theory. We now move the sun to the blue point that I had there, and Ptolemy had peculiar prejudices for putting the sun where he put it, but the fact of the matter is that famous Indian astronomer in the 5th century had already proposed that model. And Galileo was very cagey and never talked about this, even though in the 17th century it was reinvented by Tycho Brahe, and it was called the Brahe model, where all the planets are circling the sun, but the Earth is still standing still. So clearly, nothing was proven from a scientific point of view, and Galileo should be a little ashamed of making overstating the arguments, although certainly it is true that there are aesthetic reasons why we might have preferred to have the sun standing still. In terms of, by the way, the number of epicycles, remember the epicycles? You always hear that Ptolemy's model was overburdened when it was perfected. It had something like 80 epicycles. And by that time, the sheer burden of epicycles brought down the Ptolemaic theory, and Copernicus' theory rose. Well, it's all garbage, absolute garbage. There are no 80 epicycles or anything of the sort. But you repeat something often and often, and it gets into all the textbooks. And I've seen this statement of 80 epicycles repeated on and on. Now, my beloved Hooke was the first one who had a good idea in determining from observations whether the Earth is moving or not. And he wrote a book about it. Usually a very short book. This book is only about 20 pages, but published it. And how was he going to determine the motion? Well, here is the setup. He built a telescope in his own bedroom. In those days, you could make holes through the walls, and so here's his house, okay? And he has this telescope, a vertical telescope, and here's the lens. And Hooke would lie down here and look straight. There was no tube. He could just look straight through with lenses and focus on a star. And the idea was that if you are at, say, during the course of a year, if you're moving around the Earth and you're on opposite ends, then you would see a phenomena we call parallax. Like, when you put your finger in front, everybody put their fingers in front, close one eye, then the other, one and the other. You see things moving because you're seeing from two different perspectives. So this phenomena of parallax would tell him. Now, Copernicus was aware of it, and the absence of it, he argued the absence of parallax was that stars are very distant, but now Copernicus was trying to look at things with the naked eye, and now we have telescopes developed in the scientific revolution, and that allows us to see much farther. If you read the book, you see that Hooke was unlucky. After spending a lot of effort in building his telescope, he made a few observations, and then guess what? The lens from the top here fell, and of course it broke. And he had so many other interests and duties, and he had to go here and he had to go there. He had to survey and what have you, and so he never got back. But he did report a change in the position. And only in 1726, his observations were repeated identically this way with this method by Bradley, who discovered the change not due to parallax, but the phenomena called aberration, which changes the angle. But if you like, either way, it demonstrates that the Earth is in motion relative to the Sun. So it was that observation, plus what's known by the time, that but the inspiration of Bradley, by the way, and I don't know how well known that is, was due to Robert Hooke. I should say, stop here for a moment and say that one of the things that UCSC, this is one of the best kept secrets, and I hope everybody here keeps it secret too, has one of the most magnificent libraries in history of science, particularly astronomy. And the reason is, of course, that we inherited the entire Lick Observatory library. And not only that, it's on open shelves. So for the 40 years I've been here, I wander around and I look at these old books. They're fascinating and they're so full of interesting things. And nobody looks at them because I have some of them out for decades and they have never been they have never been recalled. But I have to share this with you. I mean, just don't spread it out because but it is due to that. And so I run into the memoirs of Bradley, and I was astonished when I opened the memoirs of Bradley that the first picture I saw was that picture. It's right there in his memoirs. He clearly used, I don't know how well known this is in the community, but I certainly was unaware of it. Let me say a few words about Kepler, because Kepler, of course, as you know, used the magnificent observations of Tycho Brahe and finally came to the conclusion by fitting the observations of Brahe, which were now an order of magnitude better than any before, that the motion of at least the planet Mars was a motion in an ellipse. And he published his results, and there we see the discussion of the ellipse. A little less known fact about Kepler, which I thought I'd bring up, is that a few years ago we heard that an astronomer at Lick Observatory discovered, this is the motion of Mars, let's forget about that, discovered that Kepler wrote horoscopes. I mean, in those days, probably making a living wasn't such an easy thing, so writing horoscopes by the great mathematician was part of the game, and this was actually found in the Lick library right there in the, I forgot the name of the, yeah. And there was an exhibit, and I won't go into it. But there were other problems Kepler had to face. His mother, for example, who was accused of being a witch. I mean, I want you to remember the times and the changes that the scientific revolution brought about. And witches were, I read, over 1 million witches were burned or killed in one form or another. Women were killed who were accused of witches. It was very easy to accuse a lady of being a witch, and it was very hard to disprove it. The Dutch, always very ingenious, figured out a method to determine whether a lady was a witch or not that had been accused. You weigh her. See, you have to, if you're a witch, then you have to be able to fly on a broom. So if you're very heavy, if you're very light, you're a witch, in which you're very heavy. So people who didn't want to be accused of being witches used the scientific method and traveled to outer water. My wife and I went there, and I think she decided that we should both weigh ourselves just in case, right? So we both have certificates. What you would get is a certificate from them, and once you had a certificate, you were safe against accusations of witchery. Now, we already have seen from Tony's introduction But I wanted to read the preface, because there again you see the philosophy on which the science is based. The basic problem of philosophy of science seems to be to discover the forces of nature from the phenomena of motion, and then to demonstrate the other phenomena from these forces. I mean, first you have to discover things, but the important thing, as I said at the outset, is prediction. Science that doesn't predict anything, just explains things, is yet a science to be. It's when you make a prediction and the prediction comes about. Science allows you to look into the future, something man always wanted to be able to do, and now the scientific method. And this was, of course, the very preface, and of course we know it. Great. By the way, Newton was asked, well, where is God in this philosophy? Because now you have forces and the planets are moving around and everything is understood. And Newton, who was also very, very religious, said, well, you know, there's a problem. How do you set the initial conditions? And it must have been God who set initial conditions, and that made all the preachers of the time very happy, as is seen in this letter to the Reverend William Durham. Unfortunately, we now have our astronomers and astrophysicists today trying to explain the initial conditions. This is still a major problem of the initial conditions that led to the planetary motion. Now, of course, we have, well, close to 200 planetary systems that have been observed, and all of them have different initial conditions. So clearly, the initial conditions have to do with somewhat random, but it is a major work of current research to answer the question of initial conditions. And of course, we're now talking about initial conditions, not just of planetary system, but the whole universe. You know that Steve Hawking had an audience with the Pope, and the Pope asked him, you know, what are you doing? He says, well, I'm working on the Big Bang and the explosion of the universe in the first blah, blah, blah milliseconds. Paul said, that's okay, young man, but what happened before that? That's my domain. So initial conditions are going always back in time, but the initial conditions are always there. Okay, my wife is pointing out that I'm over time, so I'm going to hurry through, but I'm going to tell you now a particular example of the scientific method and how disputes and so on are resolved. This is a portrait of Boyle I made recently while I was in London. It's in the Royal Society. And again, I want to read you what he says in the preface of he says, in the preface of his description of the experiments, he says, to know something which you did formerly but suppose, and shall present, if not with new theories, at least with new proofs of such as are not yet become unquestionable. Scientists don't jump and say, you know, here's the theory and it's absolutely right. And no. Initially, it's a hypothesis. It fits experiments. Good scientists are very cautious, and they need to be replicated. The experiment needs to replicate it, and the theory needs to be checked. And only after a long period, where many people repeat experiments and so on, that finally your explanation of theory enters the domain. And you know, the word theory remains, and some people think that a theory means that, well, it's just not quite the same thing as a fact. Let me tell you to begin. I reminded you that Galileo had an explanation for how you can suck on a tube and lift water. And he actually describes this, and here is a page from his book, The Two New Sciences. And you see over here, imagine this is a cylindrical container, and you have removed the air out from that part, and you put some weights here, and you will find that the vacuum now, the absence of air, will hold up the weight. And he said it's being held up by la fuerza o resistencia del vuoto. I mean, the force of the vacuum, the dark energy, as we would say today, is holding up this weight. Well, what happened next? Oh, the experiment was done and repeated, and here you see that indeed, you empty the cylinder from air, and you put a cap on it, and you can put lots of weights, and it holds. Now, people notice when you try to suck, as you see, I have no problem sucking on a little tube like this, but if you wanted to suck with a pump water from a deep well, people discovered there was a limit to how deep the well could possibly be. And in fact, there was about, as he says, about 18 cubits, which is roughly 10 meters, 30 feet. So the vacuum force is limited. And Galileo believed that the vacuum force, in fact, held everything together, and that gave you a measure of it. He had a student or a disciple or Vincenzo Viviani, who was Italian too, and he communicated this to Cesare Berti, who then made a beautiful experiment to verify the limit. And what he did, I show you over here, he essentially had a tube, a long tube, about 40-foot long tube, and there was a stopper at the end of the tube, and he filled it with water, had a little container below, okay, and then he closed the top and he opened the bottom. And that column of water fell roughly to 18 cubits, verifying the limits that the vacuum that was created here, as Galileo said, was holding the thing up to, that's the maximum force. This is, I think, Berti's picture, and of course here is a version of it showing a real tube attached to a house, a very nice painting of it. Now, you don't hear about Berti, you hear about Torricelli. In fact, Torricelli learned from Viviani about these observations, and Viviani told Torricelli that from this wrong theory, which we now know is wrong, of Galileo's, that if you can hold up 30 feet of water with the vacuum, then if you use a heavier fluid like mercury, it would only be 30 inches. And so why not do the thing with mercury? And that's what Torricelli did. Well, Viviani actually did the experiment. Torricelli wrote it up. But everybody forgets now Viviani and only remembers Torricelli. And you can see there the tube, and you fill it up with mercury, and then you you hold the bottom of the tube. This is a glass tube. It's closed at the top, and then you open it at the bottom, and you have a container full of mercury. And the mercury is held up 30 inches, just like Galileo had predicted. By the way, I should say that an important thing, of course, in fairness to Torricelli, is that he did not think that there was the vacuum that was holding up. He pointed out that a better explanation was that there was the weight of the atmosphere. The atmosphere was acting on the outside, which was open, of course. So the weight of the atmosphere on the outside was holding up this column. And he talked about the weight in his letter to his friend. And it's this letter which I think is the source for the credit. So Torricelli gave the first, if you like, correct explanation. It's not there is a vacuum force, but it's the air pressure on the outside that holds up. And of course, that's the basis of the barometer. This is the mayor of Magdeburg, Otto von Guericke, who decided to give a spectacular demonstration of this enormous pressure. We don't feel, by the way, the pressure of the air. If there is the weight of the air, why don't we feel it? Don't feel anything. Do you feel the pressure of the air? I don't. But that's because we have air inside as well as outside, so there's an equilibrium. Somebody pumps out the air inside, you would just totally collapse. So that's why it took ages to realize this, but this is, of course, the well-known and famous experiment where you empty the air inside two sides of a sphere, you split in two, and then you put it together. There's no air inside, pump out the air, and now, even a band of horses can't separate it. Enormous force, literally a ton. I just got last week a copy of the catalog of the Deutsche Museum, and apparently the Magdeburg spheres were real, and they are supposedly, I don't know if they're the actual originals, but there they are. Finally, let's come to the famous experiment. I have to move on. This is a replica. This is a replica of Hooke's air pump. And it has a glass container, and then you have a stopper here, and you have a pump, which is manually used. And the idea of Boyle and Hooke was to put a Torricellian column. This is from our own lab. I just made a Torricellian cube by taking a little inverted cylinder, filling it up, and then you see it holding up. Now, if we put this inside the Hooke vessel and we start pumping the air out, what should happen? If the theory that it's air pressure that is holding up the thing and we remove the air, it should fall. Now, give me a second. Unfortunately, by the way, I was not allowed to play with this pump, so we had to cheat and do it with our own local pump, and with the help of a colleague, Fred Kuttner, we repeated the experiment. And if you give me a second, I wanted to show you the So what I'm going to show you is what happens to a column when the air is pumped out. I hope it's visible in the back, but I want to make an important point. If you really want to understand what the old-timers were doing, the best way to do it is to replicate it as closely as possible. I've been doing that for years, and it's given me a lot of insight to do this. Historians can't manipulate apparatus, so they are left out of this game, but you want to do it. So you see that as you pump the air out, the air inside of the column falls, right? Because the outside pressure is decreasing, and now, in fact, you see something, however, unexpected. Look at what's going on now. It's kind of a bubbling here, huh? Look at what happens when we finally pump the thing all the way to the bottom. what do you see? You see air coming out, bubbling like crazy. Now, if you read what all right, let's stop this. If you read what Boyle was aware of this air and didn't comment much about it. Huygens replicated the experiment and decided to get rid of the air. So let's just go back to, fortunately I have to go back and forth because these darn movies are gigabytes. And if you put them on anyway, let me not bore you with that. Christian Hoyle, the way, of course, this was very exciting. And Huygens was a great scientist. Immediately, decided he needed to build a pump himself and check everything out. So he did. Of course, he had a little trouble building a pump. It was often you need to go to the person who does something and help explain. But he built a pump, and he pumped out, and he did notice that some bubbles of air were forming. He thought it was a good idea to get rid of the bubbles before performing the experiment. And guess what? He pumped and pumped, and the water wouldn't come down. So now we have a new phenomenon, and there's a disagreement, and there is a huge back and forth correspondence between Boyle and Hooke and Christian Huygens, who didn't see he was exhausting the air and it didn't come down. What's the explanation? Well, Chapin and Schaefer wrote an entire book about this without giving an explanation. And you go in the literature, I mean, the problem was never resolved. And tonight, for the first time, you're going to hear the resolution of this difficulty. Why didn't Huygens, let's say, anomalous suspension, the historians will tell you, is due to adhesion of the molecules of water in the walls and so on and so forth. And they are just absolutely cockeyed explanations. Huygens said it's because there is plenum out there. And so he sided with the plenist on this issue. So it was a very controversial thing. The explanation is trivial. When you do the experiment, you see it right away. You saw those bubbles of air coming out. They're coming out outside, but there are also bubbles of air coming inside, right? And those bubbles of air, by the way, that's why fishes are out there, because we have lots of air in the water. The bubbles of air that come out from the inside get trapped. And guess what they do? They follow the pressure-volume relation. That means that as the air builds up inside, they're pressuring the column down. So the column is not coming down because the outside air alone is decreasing the pressure. It's coming down because there's an increasing pressure inside. Completely, like, what would Sherlock Holmes say, elementary, dear Watson, elementary. But to my total amazement, you read one account after another, and it's not pointed out that that's the explanation for this. So the point I'm trying to make is that, if you do experiments in slightly different ways, you're going to get slightly different answers. But if we understand and we continue to pursue the thing, we eventually will come to a full understanding, and that was the end of the matter. You've already seen this. So let me summarize. We're going over time. So as I said now, the summary is that science not only provides explanation, but it also makes predictions which can be tested by experiments. There were two alternative explanations for the Torricellan column: an attractive force due to vacuum, dark energy if you like, or a repulsive force due to the air pressure. When Hooke's pump removed the air, the column dropped, giving evidence that hypothesis 2, namely air pressure is what holds the thing up, is the correct one. Hooke was right and Hobbes was wrong. I think that Bill Watterson is probably not recognized as a great philosopher. I'm very fond, my kids, of course, always had all the comics of Calvin Hobbes. Hobbes is named after Thomas Hobbes. That's not a coincidence, by the way. And I always read them, too. I mean, when they weren't watching me, you know, I would take it out. I would read the comics. And as you know, Hobbes, in the Calvin Hobbes story, is a tiger, which for the adults, he's just a lifeless tiger. For Calvin, he's a life tiger, and which is reality. And Hobbes would say they're both manifestations of different realities. And I think that's really the... now, it would be a joke, except I can assure you that there are many academics in the world today who think along those lines. I found this marvelous summary, this marvelous statement in a book on the founders of geology, which I like to read for you. In science, as in all other departments of inquiry, no thorough grasp of a subject can be gained unless the history of its development is clearly appreciated. Nevertheless, students of nature, while eagerly pressing forward in the search after her secrets, are apt to keep the eyes too constantly fixed on the way that has to be traveled, and to lose sight and remembrance of the paths already trodden. It is eminently useful, however, if they would now and then pause in the race in order to look backward over the ground that has been traversed, to mark the errors as well as the successes of the journey, to note the hindrances and the helps which they and their predecessors have encountered, and to realize what have been the influences that have more especially tended to retard or quicken the progress of research. This is Westminster Abbey, where our great Isaac Newton is buried, and I know how many of you have entered it, and the first thing you see is this marvelous statue of Isaac. And over here you see his ellipsis. I think, fortunately for, in that case, the sun is not at the center, it is at the focus. I checked it last time I went there, when I went there. This is the wing inside, and I'm very pleased to note that now, if I can, I should really have to go out of here, but now I can maneuver this. Right at the end of this, next time you go, please check out Robert Hooke last year finally got his due, and they have put a little, thank you very much. Why did the water boil?
Why did it not? Why didn't it boil? Why did it vaporize?
It was vaporizing.
Why did the water not vaporize?
Well, it takes some time. It's not that vaporization doesn't happen instantly. This was only a few minutes. It was just half a minute, a couple of minutes. It takes hours, but eventually you're right. Eventually all the water would vaporize. Yeah, that's a very good question, of course. And here, let me answer that question. Yeah, sorry. Can you hear me? Or
If you put a little bit of fuming sulfuric acid in the chamber with the water, it will boil so hard it will freeze.
Yeah.
And the reason is that the pump doesn't pump the water vapor very fast.
Yeah.
And you need something that will pump gather water vapor. So if you put fuming sulfuric acid in, that will gather the water vapor, and then it will
But I think there's a very important point here in that I didn't have time to mention that obviously, and Hooke said this in the dispute, he said, if you continue pumping, if Mr. Huygens would continue pumping, if he had a better pump, even in his case, where air had been removed, it would also come down, of course. And the point is that the early pumps were not able to get down to very low pressure. And so that had to be taken into account too. And there was a lot of dispute who made the better pumps. Yeah.
Forgot to mention that Hooke also was the first to observe and name biological cells.
Right. Not the microscopic ones, but the big, he saw bigger cells, yeah.
The cells in
Yeah. But in biology, of course, Hooke is known. Actually, if you talk to people in different fields, we're all split up. Biologists know Hooke because of cells. The geologists will mention the barometer. So if you look at different disciplines, they all have heard about Hooke. Physicists know about the extension law. But the whole picture of the man is only now recently really coming into focus, and he was just unbelievable. My own research has been on the nature of the discovery of the laws of gravity in planetary motion.
Why did he fall from grace? Why was he not known in the lay literature?
Why did he fall from grace? Why did Hooke disappear?
Why does he just have a plate and everyone else has big stacks?
The fact that he got a plate is already, humongous. Think of it. This is a situation where you go to the Royal Society and you walk up and down. In fact, I did this last month, and I've been numerous times there. And the walls are full of people. Newton has several portraits, and you name who is who, and it's there. And there is not a plate, there's nothing. No recognition that Hooke lived here. So getting a plate, a little tile in Westminster Abbey, by the way, at the foot of Newton, you know who has plates? Faraday, Maxwell, Lord Kelvin, all the great physicists have marks, but that's all they get. Compared to Newton, they just get a little tile. Look.
So why did it take so long?
Oh. What do you want me to say? Because I hadn't started my work? Well, you saw I was one of the early people who got the ball rolling, but no, there's always been a club, a Hooke club of people out there who knew what Hooke had done, and there was a very concentrated small group of people who knew about him. But nothing was written, and if you don't write, and if you don't have pictures to show, imagine if you don't have a picture of what a guy looks like, you're already lost. You need the picture, and then you need to have your name recognition. And of course, Newton, if you read the correspondence, the correspondence between Hooke and Newton was absolutely crucial. I have written now extensively on the fact that if it weren't for the intervention of Newton, the intervention of Hooke in the correspondence with Newton, Newton would have written nothing. In fact, I think he would have just continued doing his alchemical studies and been forgotten. It was Hooke who activated Newton and gave him some of the tools that he needed in order to write the Principia. And this is slowly being recognized now.
Maybe we can continue these conversations then around
No,
the
excuse me.
table
Hold on for a
afterwards?
second. There's a question here.
So what does your experience with Hooke say for young scientists today? What advice does the Hooke experience give to a young scientist
My
today?
advice is try not to be forgotten. And don't antagonize. Well, antagonizing Newton, it didn't hurt Leibniz one iota, I think. But Newton had a lot of, antagonized a lot of people, but somehow some people survived his antagonism and others did not. All these instruments I've shown you, Newton had, I mean, Hooke had all these instruments. Nothing has been kept, nothing has been preserved. Well, I think that the refreshments, right, are getting cold.
Thank you.